Okay, here is the video explaining the technique of integration by substitution, and I have actually four examples here for you. Probably could find a lot more. This is something that you just need to spend a little bit of time with, and eventually you're going to get it. I tried to use some colored pencils to illustrate you. It's almost a skill you acquire of being able to look at a an indefinite integral in a certain way in order to identify the technique. And the big indicator is a composition of functions. So if you look at this integral, notice we have a linear function, 8x minus 18 on the inside, but yet an outer function, which we could look at as x to the fourth. So you know that you're going to need to do something other than just recognizing a polynomial and using the power rule in reverse. And so um, what we do here is essentially identify, just as I said, the outer and inner functions. And so what we'll do is we'll let the inner function be a variable, and typically we use u. It's just a traditional variable we use. And I wrote this wrong here because if I make that substitution for u in this place, now I've got, a variable u here, but I also still have the variable x with this dx, and that's why I wrote wrong here. So I need to be accountable for, when I make the substitution for u here, what about the 8 and the dx? Well, if I come over here and take a look at this in terms of the differentials, we can break up this, and this is what's nice about this notation for derivatives, is that if I use the du dx notation here, when I take the derivative, I can just multiply both sides by the differential of x. And now I actually am accountable for the 8 dx. As a matter of fact, I can replace it with du, right? We say that they're equal here. So now I make that substitution for u, and I have u to the fourth, and the 8 dx I just replace with du. And now I have a simple integral to evaluate here. It's just the integral of u to the fourth, and I can use the reversal of the power rule, u to the fifth over 5 plus c. I could write 1/5 times u to the fifth. It would be the same thing. And then I just replace the u again. I substitute back in for u the 8x minus 18. I just realized here this should be a 5. Okay, I put the 8x minus 18, but I didn't recopy the 5. So this should be a 5 right here. So sorry about that. Um, so that would be my solution, which would be key over here. And notice they just wrote the 1/5 out front. Here, this one's a little bit more difficult to see, but I see the composition here, so I default to, I'll let u be that value here. And sometimes it's just good to go ahead and take the derivative of u with respect to x. And when I do that, I get 12x minus 14. And notice I need to be accountable for this 6x plus 7 and the dx. Okay, so, and I just realized I forgot a 2 here. Sorry about that. This should be 6x squared plus 14x, just like I have over here. So there's really a squared right there. So, when I find that, I get 12x minus 14, but that's pretty darn close to 6x plus 7, because if I just factor a 2 out here, okay, now I got my 6x plus 7, multiply both sides by the differential of x and divide by 2. So I get essentially the 6x plus 7 times dx equal to du over 2. So I'll go ahead and make the replacement. I'll replace this again. This should be 6x squared. I forgot the 2 here. Okay, so that u goes in for that. So that's going to be u to the fifth. And I have du over 2. And usually it's a good idea just to factor that out front and then evaluate the integral. Okay. Remember, we're adding one, right? So we add 1 to -4, we get -5. And I'm sorry, we add 1 to -5 and get -4. And this should be a 1 over -4. It's pretty sloppy there, okay? But that is the antiderivative of u to the -5th. We just add 1, -4, multiply by 1 over -4. So this now becomes -1/8. And then again, I will just replace the u with the 6x squared plus 14x, what I just have up here. And I'm done. And notice, again, that's what is written over here. I just wrote the -1/8 out front, but that would be the same as 1 over, and then having 8 in the denominator if I negate the whole rational expression there. Okay, so there's those two examples. If I move on here, I have a couple others. Let me just slide this up so we can see it. And let me go over here to my Promethean. I think I have number 6 and 8. So let's take a look at number 6, this one right here. Again, I look for composition of functions, and here I have e to the x, but the x is 9x cubed. All right, so that is going to be my value for u. Slide this over a little bit. So, when I look at this and say, okay, well, I'm going to let u be this value here, what's left over? Well, I have a 3x squared dx. And notice if I take the derivative of the 9x cubed, I'm going to get x squared. So that gets me on track. So let's just go ahead over here. And obviously I have this all written out, but this is just, my thinking. I'm going to let this be u. So I find the derivative of u with respect to x, which is 27x squared. I multiply by the differential of x. I need to be accountable for 3x squared dx. I have 27x squared dx. Well, I'll just divide both sides by 9. And when I do that, 27 divided by 9 is 3. I get what I need, which is 3x squared dx. So that's why I divided by 9. 27 divided by 9 is 3. I got the coefficient that I needed here. So now I'll make the substitution. This purple stuff right here, 3x squared dx, gets replaced with d over 9, and I just have e to the u. One of our favorite integrals to calculate, right? Because the antiderivative of e to the u, just like the derivative of e to the u is e to the u, same thing with the antiderivative. So therefore, I just have 1/9 times e to the u plus c, and then I'll just go back and pop in the 9x cubed for the u value, and I am done. The last one here, kind of hard to see the composition, but my outer function is 1 over x. I know I got some other stuff in here, the 6x, but it's really 1 over x. And I'm just using that formula for the integral of 1 over x as the natural log of x, okay, or the natural log of the absolute value of x. And so what I need to do here is I need to again, let u be my inner function. So that's the 5 plus 3x squared. And there we go. And I'm going to go ahead and take the derivative of that, and I get my 6x. Well, that's pretty convenient because if I multiply both sides by dx, I have 6x dx here. So that gets replaced with just simply du. And this is my u. So I put in the 1 over u, and now I just evaluate this integral. And I see yet a third mistake here. This should be the natural log. This is just using the formula. The antiderivative of 1 over u is the natural log of the absolute value. There should be a u here, not an x. So again, I apologize. There should be a u there. Guess I'm being lazy, not rescanning a document in after I make the correction, but oh well. That's a u, okay? And therefore, I replace the u, which is incorrectly in x. I'm going to replace the u with the 5 plus 3x squared, and there you have it. Okay, and you can see that that's matching up with what my math lab says over here as well. Okay, so there you have it. Number I believe number 6, yes, and number 8 I had here in addition to the other ones I had, and you have a whole bunch of these to do, and we're still going to use the this method when we're working with definite integrals, and we'll get over, or we'll explain what those are in the next video. So hope this helps, and as always, we'll see you next video.